number 1, we have the following simplified answer of 15x squared over square root 1 minus 25x to the 6th. Number 2, we have a negative 4x over the square root of 1 minus 4x squared. Number 3, 8x cubed over 4x to the 8th plus 1. Number 4, this one's a little tricky, so you have your absolute value and your 8x. You can simplify among those, and you get negative 2. Now, I'm a little safer than Khan Academy. I personally would continue to put absolute values on my x. I would personally not drop my absolute values on the x. Yes.
Why is it that you can simplify that 8x but not the other in number 3 where it's 8?
Because in this problem, the 4x squared is being multiplied to the square root. So, okay, where here they're being added. Yep. You're welcome. Okay, number 5. So your initial formula would have left you with this, which is the chain rule. So 3 inverse sine to the 2nd. Then you had to take the derivative of the inside. So my u value was 5x squared. So the derivative of u is 10x over square root 1 minus u squared, which is 5x squared squared, which is 25x to the 4th. So you could multiply your 10 and your 3 to get 30x, and then your inverse sine at 5x squared squared all over your square root. Number 6. Seven. And 8. Okay. Any questions on that handout? So again, hopefully inverse trig functions is something you're feeling really good about. You are feeling like you're getting the grasp of these. Because like I said, we are going to continue to move on. We are moving into exponential and logs. This is actually our last unit of chapter 3. And then we move on to chapter 4, which is the application of all of these functions and their features. So tomorrow, yes. Okay, tomorrow the plan is to, oh man, where'd my pen? tomorrow the plan is to give you back your chapter tests and have some time in class tomorrow to go over them and do our lesson tomorrow as well. So again, tomorrow's plan will include giving back your chapter tests. Yes.
Are we going to have like another chapter test with this?
Yeah, but it's really small. It's like since the other test was so big, this one is on just like these 2 units, so it's more like a quiz. It's not going to be a chapter test. Yep.
How were the chapter tests?
They're pretty. I mean, I have had. Did I pause this? I did. I've had pages where the chapter tests are completely and utterly perfect, and I've had pages where they're utterly awful. If that, I don't know, not to like make you feel good or bad, like it just that seemed to be like the case. I had pages where I was like, all right, perfect, and not just like 1 or 2 kids, like several kids, and then I had pages where I was like, oh, you got this page perfect. Oh, you missed every problem on this page. Oh, that one's blank. And like, in all fairness, Mr. Mannion was kind of disappointed in some of his physics kids because like one of the calculator questions was 100% physics. In terms of like, if you didn't know the calc, you could still do the physics aspect of it, or like messing up our units. That was a big one, or not putting units.
Okay, I know I didn't finish. I know there was like one question.
So those were like just a couple of the things I personally noticed. Yeah. All right. So we focused on Friday on reviewing exponential functions and logs. We focused on solving for exponential functions and logs and creating a connection between exponential functions and logarithms. Today, we are going to look at actually finding the derivative of an exponential function. So you have a multiple choice example that says which of the following pairs of graphs could represent the graph of a function and its derivative. Which of these could represent the graph of a function and its derivative? So look at the examples and determine, based on our chart, if they match. So remember, a function that is increasing will be positive on its derivative. An original function that is decreasing will be negative on its derivative. A function that is concave up on the original will be increasing on its derivative. So go ahead, there are 3 graphs there. Compare the 3 sets of graphs to determine which ones are true and which ones are false. increasing and concave up. Its derivative is therefore positive and increasing. So example I is true. So you could have had A or D so far in terms of potential answers because 1 is true. Example B is not a graph of a function and its derivative because where example B has an original function increasing, the graph is negative. So it fails to be its graph and derivative right here. And example 3, the graph is increasing, its derivative is positive. The graph is decreasing, its derivative is negative. Where the graph reaches its max, it is at 0. So 3 is also a function and its derivative. Therefore, D is your correct answer. D is your correct answer. So, like I said, today we're looking at our derivatives. The derivative of e to the x is potentially the easiest derivative because its derivative is e to the x. The derivative of e to the x is potentially the easiest derivative because its derivative is e to the x. Using the chain rule, we have to determine when a derivative's function is not just e to the x. So if you had something like e to the 2x, you need to take into account the derivative of 2x. So the derivative of an exponential with a chain rule is e to the u times du dx, where you're going to multiply by e to the u by the derivative of u. So again, that happens if e is raised to a function that has a derivative. If e is raised to a function that has a derivative, you have to multiply by the derivative of its exponential function. And it will make sense once we look at an example. So find the derivative of the following. So I have x squared times e to the negative x. This is a product rule. This is a product rule. A product rule says it's first times derivative of the second plus the second times derivative of the first. I will say there were some problems on our quiz where we did not take the product rule when we had two functions being multiplied together, which is why I'm reiterating the importance of it now. So again, the product rule says the first times derivative of the second plus the second times derivative of the first, not just derivative of each multiplied together. So that would give x squared times the derivative of e to the negative x. So the derivative of e to the negative x by our new formula is e to the negative x times the derivative of negative x, which is negative 1. So it's e to the negative x times the derivative of negative x, which is negative 1. Then finishing out the product rule, you have plus the second times the derivative of the first, which was 2x. Simplifying these two terms, I get negative x squared over e to the x plus 2x over e to the x. Because recall, an e to the negative x is really the same as 1 over e to the x. And these are now like denominators, so I can combine them to get one singular fraction. And I have negative x squared plus 2x over e to the x. So we can combine e to the x's with our trig derivatives. So basically what we're going to do in this problem here is treat the u value as our tangent x. So recall that the formula for the chain rule is dy dx equals e to u times u prime. So since u is a little trickier this time, I wrote out that u was tangent x. I'm going to find my u prime, which is secant squared x. So my u is tan x, my u prime is secant squared x. Therefore, my derivative is e to the u, which is e to the tan x, times u prime, which is secant squared x. Now, you can't simplify this. There's no way of getting that tan x out of the exponential. The only thing you could do is rearrange the terms so that secant squared, which kind of acts like a coefficient, is in front. The e's can be mixed into a problem. The e's can be mixed into a problem. So in the case of this example here, we have a quotient rule where e to the x is in your denominator. So in order to do this problem, and this is one of those ones that students mess up because we tend to forget to take the derivative of the 3x on the e. So they'll write like e to the 3x, but they forget to multiply by 3 at the end. So ho-de-hi minus hi-de-ho all over ho-ho gives e to the 3x times, so there's your whole, d-hi. Derivative of cosine is negative sine. The exponential problem is not taking its derivative till the second part of the quotient rule. We need to take into account the derivative of the angle of the trig function, where we get 2 minus the numerator times derivative of the denominator. So that's your e to the 3x times 3. And that 3 right there at the end is the 3 we tend to forget. All over the denominator squared. What you'll notice is I have a black slash through the squared as well as e to the 3x on top. That's because e to the 3x functions as a GCF and can simplify with the denominator. So e to the 3x could be factored out and then canceled with one of them in your denominator. So that leaves me with negative 2 sine 2x minus 3 cosine 2x all over e to the 3x. Again, here's a case where you have an e with a powered exponent other than just x. So my u value is negative 3 over x. For this problem, we have to find u prime. So remember that negative 3 over x is really kind of like saying negative 3x to the negative 1 power. So u prime is our power rule, which is negative 3 times the power, which is negative 1. And then you subtract 1 from your power, making it negative 2. So negative times a negative is a positive 3. So this is kind of like 3 over x squared. So y prime equals e to the u times u prime and then to clean that up, you could actually drop your e to the u down to the denominator since it's negative, and this would become 3 over x squared e to the positive 3 over x. Okay? That is under your notes, right? Yeah, it says day 3 on the next page, correct? All right, so your homework, not incorrectly typed on Fusion, is to complete page 178, 3.9 quick review, and 1 to 10. So like I said, I will adjust that. If you did 3.8, that's fine. I'll group it into Fridays, and I'll group 3.9 in here. If you did 3.9, then you'll do 3.8 today. So that way you guys all get credit for both. Everybody does both. And tomorrow we'll go over all of that. Again, you have plenty of time today. You have almost an hour to get all of that done. So plenty of time.